Section 9.6 looks at properties of logarithms. We have 4 objectives in this section, and the first one is to use the product rule, quotient rule, and power rule for logarithms. So here are some of the properties for logarithms. Remember that in a logarithm, the base of the logarithm, which we generically call b, needs to be greater than 0 and different from 1. U and V in the properties we're going to list represent positive numbers, and R can be any real number. So if these things are all true, then the base b log of U times V equals the base b log of U plus the base b log of V. Since logarithms are exponents, this actually comes from the product rule for exponents. And this is how we get our product rule for logarithms. The base b log of U divided by V, and of course V cannot be 0, is the base b log of U minus the base b log of V. This is the quotient rule for logarithms, and it comes from the quotient rule for exponents. The base b log of U to the R power is R times the base b log of U. This is the power rule for logarithms, and it comes from the power to power rule of exponents. So we have a logarithm property of equality that says if the base b log of U is equal to the base b log of V, then U has to equal V. And we could additionally say if U equals V, then the base b log of U equals the base b log of V. These properties result because of the fact that the logarithm function is a one-to-one function. So let's look at using the properties of logarithms to expand each of these logarithmic expressions. So the base 4 log of x times y, according to the product rule of logarithms, would then equal the base 4 log of x plus the base 4 log of y. That's what the product rule for logarithms gives us. Next, we're going to use the quotient rule for logarithms. The base 2 log of k divided by 64 is the base 2 log of k minus the base 2 log of 64. We are told in our instructions, whenever possible, evaluate logarithmic expressions. So we can actually evaluate the base 2 log of 64. Remember, that's the exponent that I applied a 2 to get 64. So a log is an exponent. So this is 6 because 2 to the 6 is 64. So this logarithm describes the exponent that I need to apply to 2 to get 64. And so that exponent is 6. All right, here I'm going to use first the product rule. I have the natural log of 5e squared. So the product rule tells me that'll be the natural log of 5 plus the natural log of e squared. Now remember, a natural log is a logarithm whose base is e. So what this second term says is that this is the exponent, since the base of the log is e, this is the exponent I apply to e to get e squared. And that, of course, would be 2. So here we're using the inverse property of logs and exponential functions, as well as just the definition of what a logarithm means. Remember, it always represents an exponent. What exponent? The exponent that I apply to the log's base, which in this case is e, to get whatever is in this input position. So what exponent do you apply to e to get e squared? You apply 2. Right here, I have the natural log of e to the 7th divided by y. Using the quotient rule of logarithms, that's the natural log of e to the 7th minus the natural log of y. And since the natural log of e to the 7th is the exponent that I apply to e to get e to the 7th, that logarithm actually equals 7. So this is 7 minus the natural log of y. So when I apply a natural log to e to some power, the result is always that power. The natural log and the exponential function whose base is e are inverse functions of one another. All right, now here I have to remember what we learned back in chapter 7, that radicals can be written as exponents. So we'll do that in a minute. I'm going to use the quotient rule of logarithms, and the base 5 log of the square root of 5x to the 5th divided by cube root of 25y to the 4th is actually the base 5 log of the square root of 5x to the 5th minus the base 5 log of the cube root of 25y to the 4th. And so now I want to simplify this as much as is possible. But the first thing I'm going to do is I'm going to rewrite these radicals as exponents. So a square root, which is being applied to 5x to the 5th, is a power of 1/2. A cube root, which is being applied to 25y to the 4th, is being applied to, is the same as a power of 1/3. So remember, a radical is the same as the power, which is equal to 1 over the index of the radical. Okay, so I'm then able to use the power rule of logarithms. This power is 1/2, so 1/2 times the logarithm is the same as the base 5 log of this expression to the 1/2. Similarly here, 1/3 times the logarithm, whose base is 5, times 25 to the times y to the 4th, says the same thing as what I have written above. Okay, so I now can again use the product rule. So 1/2 gets multiplied by the base 5 log of 5 plus the base 5 log of x to the 5th. So notice I'm using the power rule again. The product rule again there. Minus 1/3, I'm going to use the product rule again here. And notice how I'm bringing in this grouping, because in the previous work that I did on this step, the 1/2 really gets multiplied by both the base 5 log of 5 and the base 5 log of x to the 5th. Here the minus 1/3 gets multiplied by the base 5 log of 25, as well as the addition of the base 5 log of y to the 4th. And now I'm going to evaluate the logs I can evaluate, and I'm going to use the power rule. So I have 1/2 times the base 5 log of 5 is the exponent I apply to 5 to get 5, and that's 1. So whenever the base and the input to the log, which is this 5, whenever they're identical, then the result is 1, because that's the power I would apply to the base to get the base. Here I have plus 5, I'm using the power rule, times the base 5 log of x, minus 1/3, and let's evaluate the base 5 log of 25. That's the exponent I apply to 5 to get 25, so that's 2. Plus, and here I'm going to use the power rule of logarithms. The base 5 log of y to the 4th is the same as 4 times the base 5 log of y. And now I'm going to simply distribute. So 1/2 times this sum is 1/2 times 1, which is 1/2, plus 1/2 times 5, which is 5/2. We think of 5 as 5 over 1, times the base 5 log of x, minus 1/3 times 2, which is 2/3, plus negative 1/3 times 4, which is actually going to be negative 4/3 the base 5 log of y. And I can combine 1/2 and a minus 2/3. Okay, so this is equal to 1/2, which is the same as 3 over 6, minus 2/3. So here I multiply top and bottom by 3. Here I'm going to multiply top and bottom by 2, and I get a negative 4/6, plus 5/2 times the base 5 log of x, minus 4/3 times the base 5 log of y. And 3/6 minus 4/6 is negative 1/6. All right, and that's how I would expand that using the log properties. Right, and so now let's look at number 6. And here I have a common log. So when I see log and no written base, it's understood that the base is 10. So what I'm going to do is use the quotient rule on this. The common log of 10x cubed minus the common log of x squared minus 25 to the fourth. And this is equivalent to what the original problem is. I'm using the rules of logs to write an equivalent statement that's in a different form from the original statement. Now I'm going to use the product rule of logs. Common log of 10x cubed is the common log of 10 plus the common log of x cubed. Minus, and I can actually write this as a product. So x squared minus 25 is x minus 5 times x plus 5. And that whole thing is being raised to the fourth power. So this is equal to the common log of 10. Remember, the base of this log is an unwritten 10. So the power I apply to 10 to get 10 is 1. Here I'm going to use the power rule of logs. Common log of x cubed is 3 times the common log of x. That's what the power rule gives us. Okay, the common log of this product to the fourth power is the same as 4 times the common log of this product. And now I can use the product rule on this last expression. And I can write this. Now notice how the minus 4 is going to get multiplied by the expansion. And the log of this product, which I'm going to put in brackets, is the same as 4 times the log of the first factor in the product plus the common log of the other factor in the product. All of this is multiplied by 4. And so in this case, I don't have anything that I can simplify that I haven't simplified already. I already simplified the common log of 10. So this is 1 plus 3 log x minus 4 common log of x minus 5 plus 4 times the log of x minus 5 times the log of x minus 5. All right, so that's how we use the properties of logarithms to expand a log expression.